Solid Edge with synchronous technology extends the power of synchronous modeling to the process-specific environment of sheet metal design. Here we're going to be designing the pulley cover for our mower deck. We'll start by using the rectangle by center command, a very powerful sketching tool. We can even specify the size of the rectangle. Rather than adding dimensions, we can specify it up front. With grab and go tools, we can quickly turn the sketch into a tab using its region. The thickness of the material is set in the material table. Changing the gauge of the material changes its thickness. Again, using some grab and go tools, we can quickly and easily select the 3 thickness faces and drag them into flanges simultaneously. Solid Edge determines which flange should contain the bend relief automatically. A dimple can be created using a process-specific procedural feature. Simply select the region and give it a direction. Notice as we add PMI dimensions that the Smart dimension automatically finds the theoretical intersection of the bends to give the true outside dimension, even though we only selected the edges of the bend. With synchronous technology, we are not limited to only specifying the overall outside dimension like other CAD systems, but instead we can drive our design by either specifying the outside or the inside dimension for the sheet metal part. As we turn on the background components, know that we have some interference. To fix the interference problem, we can just add another process-specific feature of a jog to our part. The power of synchronous modeling enables us to select the jogged face and, using the powerful steering wheel tool, rotate the face into position. Next, we want to close the gap that's in the back of the part. Just simply going to drag another flange. Powerful relationship tools can be used to align the flanges to be coplanar. No specific angle information is needed, just a few mouse clicks to define the relationship and the face to match. By offsetting the steering wheel tool from the thickness face 1 mm, we can quickly establish a 1 mm gap between the 2 faces by selecting a key point during the drag and edit of the thickness face. Again, we can drag 2 flanges simultaneously using the grab and go tools of synchronous technology. We can use the same technique as before to relate the thickness face to be coplanar with the flange face. By locking the dimension to the flange, we can preserve its width as we rotate the side face. Note how Live Rules maintains the coincident faces of the inside face of the flange and the thickness face of the back flange. Next, we want to create some clearance holes for our bolts. In a true top-down design, we can use the background parts as reference for creating these offset circles that we'll later use for a hole. Now we'll simply select the regions created by the circles to create the holes. You can select the region on both sides and then simply drag downward to create the holes. Just like in synchronous part modeling, we can add dimensional control at any time to our design. The unique dimensional direction control allows us to move faces in either direction, giving us complete flexibility in our design. Here I'm going to pull the top face down. Then I'm going to switch the arrow and then change the dimension again and push the bottom face even lower. This kind of on-the-fly flexibility is not possible in a history-based system. So again, we'll use synchronous technology and move the thickness face to be even with the top of the flange. Once again, we're going to use grab and go tools to rotate the top of the pulley cover to add some clearance between the pulley and the cover. The steering wheel can even be used to rotate a thickness face into a new position. When locking to a sketch plane, notice how we can choose which edge we wish to align the X and Y directions to. Creating a closed sketch enables us to drag the interior regions to completely cut through our part to remove unwanted material. Here we're going to use the option for through all. Now we can grab those thickness faces and we can actually adjust this opening in our sheet metal pulley cover. Because the dimple is a procedural feature, we can edit its profile to drastically change its shape. And in this case, we're going to even delete the original profile and create a brand new one. We're going to use the project to sketch command to project the edge of the belt up to the profile plane for the dimple. By selecting the edges of the belt, we can create a profile that matches our belt exactly. Solid Edge allows us to use open profiles, and in this case the dimple profile is an open profile. We specify the direction and it automatically adds the dimple in the correct location. The next procedural feature that we want to add is an etch. We create an etch by simply creating a text profile first. And in this case, we're telling it that this is not a step. We want to etch this text directly into the sheet metal part. Once we place the text, we run the etch command. We have a few options in the etch command, and then simply select the text, and that text now becomes an etch feature in the sheet metal part. Now that we have the 3D sheet metal model, we need to show this in a flattened state for manufacturing. Solid Edge is able to easily flatten this complex sheet metal part and even gives us the overall size we need to order stock to build this part. We also want to add a tab feature to our flattened sheet metal part. This tab is a manufacturing tab, meaning that is available in the flat for manufacturing, but then will be cut off in the 3D model when it is bent. So here we're just creating a profile that represents this tab. I don't want to violate my overall size, so I keep the tab inside of the blank size. We also have the ability to change the representation of the deformed sheet metal features. In this case, the dimple, I want to show as a feature profile and also show the origin. Return back to the bent state of the model and notice that the tab, the manufacturing tab, has been removed. By adding a bend table, I'm able to show the bend sequence. I can even change this sequence. Here I have bend 8, and I want that to be the first bend that I create. So I simply move it up the table to the top and it becomes Ben 1. Next, we're going to use a quick sheet template of predefined views to create the draft file for this sheet metal part. This is going to contain a flat pattern as well as the model in the bent state in an isometric view. I'm going to dimension this using coordinate dimensioning. I select the origin, and then as I pick edges or lines, it allows me to create that coordinate dimension very quickly. It also maintains the alignment between the dimensions. I can even dimension the strike point or the feature origin. By clicking on the Alt key as I click, I can create a jog in my extension. This is also easily adjusted with handle points. Adding the bend table that we created in the 3D completes the loop for manufacturing. I have some options within the bend table to add a title, and in this case we're going to call it the pulley cover. I have all these different options as well as in the bend callout. I also want to show the bend direction and also the bend angle in the callout for each bend. As I zoom in, notice the callout on the bend sequence, the direction, and the angle. We can even include the included angle in the bend table. Solid Edge with synchronous technology enables the user to create highly editable, complex sheet metal parts quickly and easily. And just like synchronous part modeling, edits can be made quickly and easily without fear of downstream features failing due to history in the model.